One of the cornerstones of a democracy is the right of citizens to participate in elections. Voting might appear to be a simple activity of producing the winner of an election, or just a matter of counting the votes correctly. But there is more behind election exercises, and many experts, like the mathematicians, devote their professional careers to this field of study. Now let us examine the mathematics of voting. Voting theory falls under the area of social choice theory, which deals with the process by which varied and conflicting choices, as in elections, are consolidated into a single choice of the group or society that reflects the desires of each individual as much as possible. In 1952, the mathematical economist Kenneth Arrow wrote a seminal paper titled Social Choice and Individual Values that examined the fundamental concepts of this theory. In particular, Arrow proved an important result that addresses the question, is there an ideal voting system? A voting system is a way for a group to select one winner from among several candidates. The mathematical concept underlying voting systems is that of order. There is an area of mathematics called order theory that studies ways in which objects can be ordered, from simple ordering of integers from smaller to bigger, or ordering of subsets of a set via inclusion, to more complicated relations. Voting system is ranked or preferential voting system, wherein the voting system asks how voters rank the candidates as in survey of preferences. Under any voting system, there are some conditions or features that are needed to be satisfied. One of which is the assumption that voting systems are transitive. A voting system is transitive when the relative preferences of the voter are not altered by the elimination of one or more candidate. What happens when a voting system is non-transitive? Consider an election with three candidates A, B, C, where the voters are asked to rank the three candidates according to their preferences. As shown in the table, 1/3 of the voters ranked A as first, B as second, and C as last, while the other 1/3 of the voters ranked the candidates B, C, A, and another 1/3 of the voters ranked the candidates C, A, B. Taken in pairs, 2/3 of the voters prefer A to B, other 2/3 of the voters prefer B to C, and another 2/3 of the voters also prefer C to A. This non-transitive situation is problematic because no candidate stands out. Going back to the transitivity condition of voting systems, if a voter prefers candidate X to Y and Y to Z, it is reasonable to assume that the voter prefers X to Z. It is only in this sense that individual preferences are assumed to be transitive. Looking at the example from before, it does not satisfy this condition, hence the non-transitivity can cause problems. Aside from the transitivity condition that voting systems should satisfy, the second condition would be the fairness condition or principle of the voting method, which will be further discussed later on.
Now that we have an idea on what voting systems are, we move on to the six major conditions which could establish their fairness. In the language of voting theory, there are principles of fairness that a voting method may satisfy or violate. These are desirable conditions that would manifest being fair in elections or would make them positive from the point of view of the voters. First, we have the Condorcet criterion. This fairness criterion states that if there is a candidate who wins in a one-to-one comparison with any other candidate, then that candidate should be the winner of the election. This principle of fairness is coined from the French statesman and scholar Marquis de Condorcet, a leading figure in the French Revolution who wrote on mathematics, political science, economics, and human rights. The majority criterion. This criterion states that if there is a candidate that is the first choice of the majority of the voters, then that candidate should be the winner. The monotonicity criterion. This principle of fairness states that if a candidate X is the winner of an election, and in a re-election, all voters who change their preferences do so in a way that is favorable only to X, then X should still be the winner. Independence of irrelevant alternatives criterion. This principle of fairness states that if candidate X is the winner of an election, and one or more candidates are removed and votes are recounted, then X should still be the winner. Unanimity. This criterion states that if every individual prefers a certain option to another, then so must the resulting societal choice. Lastly, non-dictatorship. This fairness principle states that the outcome of voting should not simply follow the preference order of a single individual while ignoring all others.
Now, let's move on to the different voting methods and the present problems they have with the discussed fairness principles. But first, what do voting methods even mean? They refer to the mathematical process, algorithm, or manner in which individual votes are counted and consolidated to produce a winner. It's important to note that this does not refer to voting machines, polling precincts, absentee voting, or the like. But for you to better understand, let's take an example. In a certain barangay, 37 residents selected the barangay leader. There were 4 candidates A, B, C, and D. The voters were asked to rank the candidates and the individual votes were then consolidated. The consolidated results are displayed in the table below called the preference schedule. And from the 37 voters, 14 people ranked their preferred candidates as A, B, C, D, while 10 people ranked their candidates as C, B, D, A, 8 ranked theirs as D, C, B, A, and so on. The top row being their first choice. Using this table, we can now introduce the 4 different voting methods and use them to arrive to our elected barangay leader winner. The voting methods actually include the plurality method, word count method, method of pairwise comparisons, and plurality with elimination method. Now let's start off with the plurality method, or what we also know as pataasan. This method is known to be the most popular method for its simplistic nature. In this method, the candidate with the most number of votes, or most first-place votes, wins. Now let's apply this to our vote. Based on the number of first votes provided, it is obvious that candidate A got the most first-choice votes, which is 14 votes. C having a sum of 11 votes, candidate D with only 8 votes, and B with only 4. Thus, candidate A wins in the plurality voting method. Moving on to the second voting method, the word count method, which is a weighted voting method where each place on a ballot is assigned points. The points are then tallied for each candidate and the candidate with the highest total wins. Now let's try it. First, we assign each rank their values, 1 point being the lowest, and multiply this value to the number of votes above. For example, let's weigh the votes of candidate A. To do this, we multiply the value of the rank to its corresponding number of voters. Thus, focusing on the votes of candidate A, we get the summation of 14 times 4, 10 times 1, 8 times 1, 4 times 1, and 1 times 1 to arrive to the total values of candidate A. We do the same methods with candidates B, C, and D to get the summation of their weighted votes. After getting the total, we will compare the weighted sum of every candidate and the highest will be the winner. And as you can see, candidate E becomes the winner instead. Observe that with this board account method, our candidate A places last. We can now move on to our third voting method, the method of pairwise comparisons. In this method, every candidate is matched on a one-to-one basis with every other candidate. When pairing two candidates one-to-one, each vote is received by the order of preference indicated by the voter. This can be easily understood if we apply it to our data. We first list the comparisons that we are gonna need, which is all candidates. We do so by comparing A versus B, A versus C, until we reach C versus D. By comparing A and B only, you can see that A is more preferred than B in the highlighted columns. Thus, A gets the summation of those votes, and B gets the votes in the columns where B is more preferred than A. Thus, we see that A is preferred by 14 voters over B, and B is preferred by 23 voters over A. B wins and gets 1 point. We also do the comparisons with A versus C, where C wins, A versus D, where D wins, B versus C, where C wins, B versus D, where B wins, and C versus D, where C wins again. We compare all pairs and see who won most rounds, and in this case, candidate C has the most points, having 3 points or having 3 wins, which makes him or her the winner for this voting method. Lastly, we have plurality with elimination method. This is just a more sophisticated version of the plurality method and is carried out in rounds. The method starts by eliminating the candidate with the fewest number of first place votes. By this, we remove from the preference schedule that candidate with all votes assigned. The process is repeated round by round until candidate with the majority of first place votes emerges. First, we look at the candidate with the least first place votes, which is B, since the candidate only has 4 votes. We can now eliminate B from the table, leaving us spaces in different rows. We just fill those in by ranking up those candidates below B upward, leaving us with a table that contains first to third choices of votes only. We can now merge the columns with similar rankings, such as the highlighted column CDA having a merged 11 number of votes, and also DCA having a merged 12 number of votes, thus leading us to a reduced table. We do this again by eliminating the next candidate with the least votes, which is C for this case. We then eliminate C and combine the identical second and third columns, leading us to round 3. Since A has lower first place votes than B, we eliminate A, leaving candidate D with 14 plus 23 votes, which is 37 in total. Thus, from the 3 rounds, candidate D is the winner. It is now important to note that from a single sample of election, we used 4 different methods and obtained 4 different winners. Now that we know how the different voting methods work, we can now move on to how these methods are problematic relative to the fairness principles discussed a while ago. On the given table sample 2, using the plurality method, it is obvious that candidate R is the winner. But having candidate R as the winner violates the fairness principle, that which is the Condorcet criterion, which argues that the candidate who wins in a 1-to-1 comparison with any other alternative, that candidate should be the winner of the election, since doing a 1-to-1 comparison in this sample table would make candidate H as the winner instead. Moving on to the given table sample 3, using the Borda count method and computing the weight of the following candidates, we get the following weighted points, making candidate B the winner. Now note that this outcome violates the majority criterion, since candidate A has a 6 out of 11 first place votes, a majority, but the Borda count method failed to produce A as the winner. On the given table sample 4, using the method of pairwise comparisons, we get the following points of the candidates after being compared from one another, making candidate A the winner. Let's say the Comelec in the election wanted to have a recount without new voting. Before losing the recount, losing candidates B, C, and D conceded and requested to drop the race, thus their votes were omitted. This means the new preference schedule is now presented below. And after filling the gaps and merging all the similar columns, we get this finalized table. The winner is now candidate E, but originally candidate A was the winner before candidates B, C, and D dropped the election. This violates the independence of irrelevant alternatives fairness criterion. Lastly, on given table sample 5, we use the voting method plurality with elimination. As we eliminate B having the least number of first place votes, we obtain a reduced table and observe that candidate C wins this round. Let's say the Comelec declared the election null and void due to some irregularities and asked the voters to cast their votes again. A second election is held and the 4 voters in the last column of round 1 decided to change their ranking. They switched their first and second choices between A and C, expecting to be on the winner's side after the new election. No other voters changed their choices. Since C won the first election and the new votes only increased C's votes, we expect C to win again. So let's now determine the winner of the second election. It shows here that B wins in the new election, and this outcome violates the monotonicity criterion. We have presented instances of elections using certain voting methods where particular fairness criteria were violated. Seeing the results, we then become desperate in finding the answer to the question, is there even a best method of voting? Well, most experts will declare that there is no ideal voting method. But there exists a mathematical basis for this very famous and deep theorem of the mathematical economist, Kenneth Arrow. With this, we now move on to the next section.
You might be wondering why there are elections using certain voting methods where particular fairness criteria were violated. These might lead one to ask, is there a best method? An immediate and easy declaration for this would be that there is no ideal voting method. Kenneth Arrow, a mathematical economist, actually provided a basis for this, and it is called the impossibility theorem. Arrow's theorem applies to ranked or preferential voting systems. Using concepts of order theory, the impossibility theorem demonstrates that it is impossible to design a voting system that would simultaneously obey or satisfy all of the fairness criteria in all voting instances.
Let us proceed to the second part where we will discuss weighted voting systems and the measurement of power. What are weighted voting systems? Weighted voting systems are systems where voting rights are not equally divided among all voters. An example of this occurs in corporations where each shareholder has as many votes as the number of shares owned. Here, we assume that each situation involves only two options or alternatives. A vote in this system with only two alternatives, such as a yes or no vote, is called a motion. There are three important elements of a weighted voting system. Players, which are the people who are voting, denoted by P sub 1, P sub 2 until P sub n, weight, which is the number of votes of each player, denoted by W sub 1, W sub 2 until W sub n, and quota, which is the minimum number of votes needed to pass a motion. Quota should be greater than 50% or half of the sum of the weights, and is denoted by the variable q. To indicate a system, we write the following, where q is the quota and the w's represent the respective weights of each player, and this is useful in Banzhaf index. Before we proceed to the computation of the Banzhaf index, let us define some terms. First, a coalition is any set of players that join forces to vote together, and its weight is the total number of votes in a coalition. Thus, winning coalitions are coalitions with enough votes to win, while losing coalitions are coalitions with not enough votes. Also, a grand coalition is a coalition in which all the players in the system voted together. Second, a critical player is a player who can turn a winning coalition into a losing coalition by changing his or her vote. We now proceed to the Banzhaf index and the computations involved. The Banzhaf index revolves around the idea that a player's power is proportional to the number of times the player is critical. The computation for the Banzhaf index has 5 steps, which we will demonstrate in the following example. Suppose we have the following system: quota 4 and weights 3, 2, and 1. Since there are 3 players, we name them A, B, and C so that A has a weight of 3, B has weight 2, and C has weight 1. The first step is to make a list of all coalitions. Since there are 3 players, there are a total of 2 raised to 3 minus 1 or 7 coalitions and are the following: A, B, C, AB, AC, BC, and the grand coalition A, B, and C. Notice that this is very similar to the concept of the power set. The second step is to determine which are winning coalitions. For this particular case, we have 3 winning coalitions, particularly AB, AC, and the grand coalition A, B, and C. But why are they winning coalitions? Recall that a system has a quota 4 and A has weight 3, B has weight 2, and C has weight 1. So the coalition AB has weight 5, coalition AC has weight 4, and the grand coalition AB and C has weight 6, which are all greater than the quota of 4. The third step is to determine the critical players in each winning coalition. This is best achieved by trying to remove players from each coalition one at a time and examine the remaining coalition. For example, for coalition AB, if we remove A, we are left with B, which is a losing coalition, and the same is true if we remove B instead. Thus, A and B are both critical players. The same is true for coalition AC. However, notice that for the Grand Coalition, if we remove A, we are left with coalition BC, which is a losing coalition. So, A is a critical player. However, if we remove either B or C, we will still have a winning coalition, so they are not critical players. Hence, for the Grand Coalition, A is the only critical player. The fourth step is to count how many times a player is critical. For this particular case, A is critical 3 times, B is critical 1 time, and C is also critical 1 time. For the fifth step, we add all these numbers to get the total critical instances denoted by T. For this system, we have T is equal to 3 plus 1 plus 1, which is equal to 5. Lastly, to get the power index of each player, simply divide the number of times they are critical by the total critical instances. For this system, A has a power index of 3/5, B has a power index of 1/5, and C has a power index of 1/5. Combining this into a triple, we have the Banzhaf power distribution 3/5, 1/5, 1/5.
To further understand the process of weighted voting systems, here we give some examples of power distributions in some institutions. One is the United Nations Security Council that has a total of 15 members, 5 of which are permanent members, and they are the US, UK, China, France, and Russia, and 10 non-permanent members which are voted into the committee with a fixed term. The voting rights in the Security Council can be viewed as a weighted voting system with 39 votes as their quota, with weights 7-1 for permanent and non-permanent members respectively. Hence, the Banzhaf power index of a permanent member is 16.7%, giving all of them a veto power, while a non-permanent member has 1.65%. A winning coalition can arise if it is voted for by 5 permanent members with at least 4 non-permanent members. In the United States, they use a unique method for indirectly electing their next president called the Electoral College. The Electoral College was established in 1804 under Article 2, Section 1, Clause 2 of the U.S. Constitution that states how many electors a state can have. The Electoral College has a total of 538 electors. Each of the 50 states, including the District of Columbia, have a number of electoral votes equal to the combined total of its congressional delegation, which is described as the number of representatives proportional to their population with the addition of 2 senators. As a general rule, electors from a particular state vote for the presidential candidate who wins the plurality of votes in a state. To simplify, it follows a winner-takes-all system. Therefore, we can set the Electoral College as a weighted voting system with the 50 states and the District of Columbia as the players, with a quota of 270 electoral votes, which is more than half the total electors to win the presidential election.
Now let's proceed with Section 3, Fair Division and Appointment. So fair division. So on fair division problems, given n players and the set of goods S, how can you divide the set into n shares in such a way that each player gets a share that he or she considers fair? So the assumption is that a fair share is any share that, in the opinion of the player receiving it, is worth at least 1/n of the total value. It only matters that an individual player thinks the share is fair. based on the player's own personal value system. So the properties of a fair division scheme is that it's decisive, it is internal to the players, it assumes that the person has no knowledge about each other's value systems, and it assumes that the players are rational. So apportionment is a typical application of fair division. It refers to the process of allocating identical indivisible objects among participants entitled to unequal shares. For the definitions, the standard divisor is the average number of people per seat over the entire population. The standard quota is the exact fraction of the total number of seats a state would be entitled to if seats were not indivisible. The quota is usually not a whole number. The lower quota is the standard quota rounded down to the nearest whole number, while the upper quota is the standard quota rounded up. So there's a quotas rule that a state's apportionment should either be its upper or lower quota. Here are some quota methods and paradoxes from the quota method. First, we have the Hamilton method proposed by Alexander Hamilton in the 70s. So first, calculate each state's standard quota. Then, you initially assign each state its lower quota. Third, we give surplus seats one at a time to states with the largest absolute fractional parts until you run out of surplus seats. So for example 1, a mythical country with 3 states, A, B, and C, has a total population of 1 million. There are 100 seats to be apportioned to the 3 states. The standard divisor is therefore SD is equal to 1 million divided by 100, which gives us a total of 10,000. We will use Hamilton's method to apportion the seats.
Below are our given population sizes for each states A, B, and C, with a total of 1 million. Since the first step of Hamilton's method is to calculate each state's standard quota, we divide 1 million by each population sizes of A, B, and C to arrive at these values, having a total of 100. We round our standard quota values in the usual way, giving us a total of 101. And then we do the second step for Hamilton's method, which is assigning each state its lower quota. We do this by rounding down the values of the standard quota at all times. This gives us a total of 98. We subtract the standard quota with the lower quota to get the absolute fractional row. No need to get the total for this one. Then we do the third step of Hamilton's method, which is giving surplus seats one at a time to states with the largest absolute fractional parts until we run out of surplus seats, which is 0.7 under A and B. We can only assign 2 surplus seats since we mentioned that we only have 100 seats to apportion to the 3 states, and our total lower quota is 98, thus 2 surplus seats. Basing from the lower quota row, 65 becomes 66, 23 becomes 24, and 10 remains as 10, giving us a total of 100 seats.
Now this time, let's try using the Lowndes method. First, we start out in Hamilton's method, but assign surplus seats using relative instead of absolute fractional parts. This means we divide the fractional part of the quota by the integer part of the quota. We first illustrate the relative fractional part. So we obtain the relative fractional part by obtaining the fractional part divided by the integer part.
Now, we will apportion the 100 seats in our 3-state country in the first example, this time using Lowndes method. As the first step of the Lowndes method mentioned, we will first start out as in Hamilton's method, as shown in the table below. The only difference is in step 2, where we assign surplus seats using relative fractional parts. To solve the relative fractional parts of each state, A, B, and C, we use their standard quota values and divide their respective integer and fractional parts. For A, using its 65.7 standard quota, we divide 0.7 with 65 and get 0.01. For B, we divide 0.7 with 23 and get 0.03. And for C, we divide 0.6 with 10 and get 0.06. Like the Hamilton method, we distribute the two surplus seats with the highest relative or absolute fractional parts, which is B and C for this case, since 0.06 and 0.03 are the two highest. Basing from the lower quota row, 65 remains as 65, 23 becomes 24, and 10 becomes 11, giving us a total of 100. Now that we've discussed the quota methods, we can now proceed on to the paradoxes.
Paradoxes are applications of the quota methods mentioned earlier. A paradox is a contradictory statement that may nonetheless be true. It is an assertion that is essentially self-contradictory, based on a valid deduction from acceptable premises. Paradoxes are also often statements or situations contrary to received opinion or are counterintuitive. Paradoxes have three types: population paradox, Alabama paradox, and new state paradox. First is a population paradox. It is stated that the increase in a state's population causes it to lose a seat. When two states have populations increasing at different rates, a small state with rapid growth can lose a legislative seat to a big state with slower growth. For example, recall the allocation in the mythical country with states A, B, and C using Hamilton's method. Now suppose that the population grew to 1,010,000. Standard quotas are recomputed using Hamilton's method again. After recomputing using Hamilton's method, the new standard divisor is 10,100. Notice the absolute fractional parts of the new standard quotas of each state. State A and B both have 0.3 as their absolute fractional part. While state C has 0.4 as its absolute fractional part. On the table in the previous slide, state A gained a seat because it has the largest population. But in this paradox, comparing the three quotas, state C decreased in their population but gained a seat. Next is the Alabama paradox. It is the first of the apportionment paradoxes to be discovered. It is stated that the increase in the total number of seats to be apportioned causes a state to lose a seat. For example, after the population growth in the mythical country, the Congress decided to allocate 101 seats. In this paradox, the number of seats is increased to 101, changing the standard divisor to 10,000. Again, based on the absolute fractional part of the standard quotas, the new allocation shows that State A is entitled with 66 seats, State B with 25 seats, and State C with 10 seats. Notice how State C lost a seat with no changes in population when the House increased the number of seats. Next is the new state paradox. This paradox is discovered in 1907 when Oklahoma became a state. It is stated that adding a new state with its fair share of seats can affect the number of seats apportioned to other states. For example, a new city has two schools, Dilao and Pula. Mayor Mocha donated 100 computers that were apportioned using Hamilton's method. Now, having a total population of 10,000, the standard divisor is 100. Since the absolute fractional part of Pula is higher than that of Dilao, Pula is entitled to one more computer. Now suppose that a new school is created with an initial enrollment of 525. Mayor Mocha decided to add 5 computers to the pool of computers. Since the population changed because of the new state, the standard divisor is now 100.24, thus changing the value of the quotas earlier, from 10.45 to 10.42 and 89.55 to 89.34. Notice again the absolute fractional parts of the three schools. Dilao has a higher absolute fractional part than the others, thus entitled to one computer, and Pula losing one. Apart from the quota methods, there are also divisor methods. Divisor methods are apportionment schemes where the standard divisor and standard quotas are not used. Instead, these methods use the modified divisor, which is obtained by trial and error. It may take up some time to come up with one that is exactly fit for the given. The modified divisor is used to obtain modified quotas that result to no surplus seats. Modified quotas are obtained by using the formula below. MQ is equal to state population over MD. Now, three men developed these apportionment methods as alternatives for Hamilton's method, namely Thomas Jefferson, John Quincy Adams, and Daniel Webster. There are certain steps when using divisor methods. First, determine the standard quota for each state, that is, state population over SD. Then round off each quota to a whole number according to the following rules. In Jefferson's method, just drop the decimal of the quota. In Adams' method, round up the quota. And in Webster's method, round off according to the normal rounding rules. This is where the trial and error comes in. The divisor should be modified until the resulting sum of modified quotas is exactly the amount required to be apportioned. In Jefferson's method, suppose that 100 seats are allocated from a population of 1,100. The standard divisor is 11, that is 1,100 over 100. However, modified divisors are used. Note that the Jefferson's method uses the lower quota. When the standard quotas are rounded off to their lower quota, the resulting quotas is not exactly the same as the amount required to be apportioned. Thus, the modified divisor was used, say 10.8. The resulting sum of modified quotas is exactly the same as the required amount to be apportioned. Also take note that in Jefferson's method, the decimals of the quotas are dropped to obtain a whole number. Adams' method uses the upper quota, on the other hand, but still using the given Jefferson's method, the SD is 11. In Adams' method, note that regardless of the decimal value, the quotas are rounded up to one value. In this example, say the modified divisor is 11.2. The resulting sum of modified quotas are exactly the same as the amount required to be apportioned, which is 100. Next is the Webster's method. In Webster's method, we just use the usual rounding off of values. Retain the whole number when the decimal is from 0 to 4, then add 1 if the decimals are from 5 to 9. In this example, our modified divisor is 10.95 to obtain the exact amount that is required to be apportioned. Last is the Huntington-Hill method. The method is similar to the Webster's method, except that rounding off is based on the geometric mean, instead of the usual arithmetic mean. Geometric mean of x and y is the square root of the product of x, y.